Hello everybody, my name's Scott Essner, and today I'm going to review adaptive motion control using neural network approximations. And that is an article by Huang, Tan, and Li. So, why use an adaptive method for motion control? In motion control systems, many parameters of the plant are difficult to model accurately. Friction is very hard to model. A lot of times, in addition, you have parameters that are updating themselves over time. If you have a robot that is moving left to pick up a part and then moving right to set that part down, in those two moves, it's got different parameters for weight, inertia, and those, because those change, it's hard to choose a value that works all the time. So the example system that was used in this paper was a 1 degree of freedom system. In the end of the paper, they actually modeled a physical system which was a linear axis, as you can see in the picture here. We have the model here, which is a function of the mass, damping coefficient, a frictional force, periodic disturbances, and then you have the controller and dynamic disturbances, which are random outside disturbances. So here's our game plan. We will estimate the mass, damping, and the linear component of the friction using a simple linear least squares model. We'll then estimate the nonlinear components of friction as well as the periodic disturbances using radial basis function neural networks. And then we'll also use linear least squares to estimate the effects of approximation error and the dynamic disturbances in the model. So, modeling friction. One of the biggest challenges in this model was to model the friction of the system and do so accurately. So, as a basis, the authors started by using the friction model discussed in one of the references to the paper by Canutus DeWitt. He modeled the friction between two surfaces as a contact between bristles. So as you can see in the image, the idea was that the bristles would interact with each other and you would see a direction-dependent behavior that would show up especially when you change direction and when you were changing velocity. The bristle model captures direction-dependent behavior, such as the bending of bristles and changing direction. It also captures the velocity-dependent behavior. Bearing friction, for example, increases monotonically with velocity. In addition, it captures the stiction force, which my best understanding of it is a system that is on the verge of transitioning between the coefficient of static and sliding friction, has this stiction effect where it could potentially vary its resistance repeatedly. So you'll see here now the bristle model. You have a variable z, which is a model of the bristle deflection angle. It's modeled as a function of velocity, and then you also have the function h, which is meant to capture the velocity dependent portion of the friction. But you'll see that in this model there are 6 constants: sigma 0, sigma 1, sigma 2, fs, fc, and x dot s, which have to be modeled or have to be chosen accurately to get an accurate model of the friction, but typically you don't know those values, so it's very laborious to try to determine those values. So what the authors suggest is an adaptive friction model. The adaptive friction model using radial basis neural network will model the nonlinear function of the friction. And for ease of modeling, the centers and spans are chosen ahead of time, and they're considered constants. They're chosen so that they overlap along the span of the potential values for the friction, so that we can use a quick linear least squares update and not have to do a line search or one of the other methods. So the periodic disturbance model is almost identical to the friction model. Once again, radial basis functions. Once again, the centers and spans are chosen ahead of time. And so now we get into the estimation algorithms. The estimation algorithms can be done in a continuous time simulation and are a linear least squares. So it's worth mentioning that the error system E is the difference between the desired and actual position, and the authors claim that R, which is the filtered tracking error, is a common measurement for systems using servo motors. The value for gamma there is, in the simulation we do, it's actually 20. So it fairly heavily weights the positional error over the velocity error. So I won't go into a whole lot of detail on the stability analysis because it is identical to the analysis we did in class. The Lyapunov functions are of the form of 1/2 x squared for each of the variables, and the proof walks through the same details we went through in class to verify the stability of a general network. So, on to my model. The non-adaptive model, which we use for comparison, utilizes a PD controller, so a proportional and derivative controller, mainly, strictly for comparison. The proportional and derivative gains, as well as most of the constants, for example, the mass, the sigma values for the friction model, the model for the periodic disturbances were all givens, so I could compare to the simulation results of the original paper. There were a few details that they left out when it came to the acceleration profile that they desired, and then there weren't a whole lot of results other than the tracking error. So the Simulink adaptive model, as you can see, has several more items. Each of the subsystems in the bottom center is one of the adaptive updates for friction and the periodic disturbances, plus the delta 1 and delta 2 terms were some of the terms they used to capture the approximation error that could exist in the other functions. So, a few comments about the simulation. I compared them using the same acceleration, velocity, and position profile. And I did my best to match the inputs to the simulation in the original paper. So, for results, we have here a graph of the filtered tracking error over a 1 second move, which looking back at the position and velocity, those moves were listed over a second as well. So as you can see, the non-adaptive method has a much higher initial error, and over time it gets closer to the adaptive method, but never quite catches up. I do believe that additional parameter adjustment would probably show improvement to both controllers, but I think with tuning that the adaptive controller will still gain ground over the non-adaptive method. So my conclusions were that the authors demonstrate a stable model for motion control that accounts for friction and periodic disturbances. And I confirmed in my simulation that that is indeed the case, that we did improve over the original model. And just a few comments. As a next step, I'd like to see what a different motion profile would do, and especially one that changes direction. One of the key advantages to the adaptive controller was to get around the situation where you had so many friction parameters to deal with. And a lot of those friction parameters dealt with the bristle deflection, and that bristle deflection is dependent on direction. So I think a change in direction would cause that bristle deflection to have a greater effect, and really demonstrate how hard it is to accurately choose those constants. The authors also got to test the controllers on a physical system, and were able to confirm that the adaptive controller did improve performance. I work in a group that has access to linear stages like this, and I think it'd be a great chance to be able to try to improve the performance of these axes by carrying out a test like this myself. So I thank you for your time, and have a good day.